In my previous video, I mentioned that the next video would be about graphing piecewise defined functions, but then I realized that there was a major piece of the puzzle missing, and then I needed another video before we got to that. So in this lesson, we're going to talk about finding the domain and the range of a function from its graph. And you'll notice that I once again wrote a workshop. I have 4 examples here. I'm going to do the first 2, and then for the next 2, I'm going to ask you to pause the video for a few minutes and try it on your own, and then come back, watch me work it through, and see if you were on the right track. If it becomes clear to you as you're watching me walk through it that you were not on the right track, feel free to pause again, redo, and then see if you got there. It's very hard for me to make these videos interactive, so this is my attempt at doing it, and it requires you playing along a little bit. So play along with me. Let's make this a workshop. So number 1, find the domain and the range of the following functions. So I want to remind you that the domain is the set of all of the inputs that this function acts on. So the set of all possible inputs for this function. So when I say possible inputs, I mean these are inputs to which the function knows how to assign an output. There is a defined output that is assigned to this input. And the range, well, that's the set of all possible outputs. So, in much the same way as the domain, the range tells us what outputs are you ever going to get when you're dealing with this function. It is possible to have, and in fact one of the examples here does just that, unrestricted domain, unrestricted range. What do I mean by that? All real number domain, all real number range. Looking at the 4 graphs, see if you have a suspicion. Which one is the one that has an all real number domain and an all real number range? So kind of pick one, they're all numbered, pick one, and see how we do. So I'm actually not going to start with the very first problem. I'm going to start with problem number 3. So you'd think I'd go in order, but I'm not going to. I'm going to start with problem number 3, and we're going to start talking about its domain. So remember, when we look at points on a graph, the inputs show up as x-coordinates of points, and the outputs show up as y-coordinates of points. So what I like to do when I'm talking about domain is I like to trace along the x-axis and ask myself, is there a point on the graph that has this x-coordinate? What do you think as I'm moving along so far? If I pick this point, for example, is there a point on the graph that has this as its x-coordinate? Nope. You scan above, you scan below, there is no point on the graph with that x-coordinate. And the same is true for any point here, any point here. I'm moving along, I'm moving along, I'm moving along. No points so far. It's not until I get here that I finally have a point on the graph with that x-coordinate. So the domain starts at 4. So I'm going to very clearly label this point as having x-coordinate 4. That is the beginning of the graph. The picture was completely blank until we got there. From here on out, how's it looking? Well, if we trace along the x-axis, it seems like for the rest of the time, there is a point on the graph with that x-coordinate, because if I pick any point to the right of 4 on the x-axis, I can find a point on the graph with that x-coordinate. Now, I don't like putting arrows on my graphs. It's kind of a flaw of mine. I think it makes graphs look clunky, but you'll often notice little arrows on the edges of the graph to indicate this graph goes on likewise forever. So the reason that this is valuable is that you can assume that the graph isn't going to go do something weird like stop or loop back around or do anything like that. So we are given this picture of the graph and we are told the graph continues on in this fashion. It doesn't really break pattern from here on out. Anything that was going to happen has happened. So the domain of this function, like we just said, starts at the number 4 and then goes from there. Now you'll notice I'm writing it in interval notation. So because it goes on to infinity, we put a parenthesis around the infinity symbol. Infinity cannot be included, it's not a real number. But there's a real question, do we include the 4 or not? And that question is answered by this. There is actually a point there whose x-coordinate is 4. So that means that, in fact, 4 is part of the domain. Now let's think about the range. So, as we talked about in both of the last 2 video lessons, outputs live on the y-axis for our purposes. So much like I traced along the x-axis talking about the domain, I'm going to trace along the y-axis talking about the range. So there I go, 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 there I go. So far nothing, right? If I pick any of these y-coordinates and I look side to side, there is no point on the graph with that y-coordinate. It is not until I get here that I finally see a point with that y-coordinate. There it is. So much like the domain started at 4, the range doesn't start until 2. So the range starts at 2, and then again, this graph starts here and then it goes sort of likewise indefinitely. So the range starts at 2. There is an actual point on the graph whose y-coordinate is 2, and then it goes on from there forever. So we would write the range in interval notation as starting at 2 and going to infinity. Okay. So the next problem I'd like to look at is number 1. So for number 1, we do exactly the same thing. We start tracing along the x-axis, and what you're going to notice right away is, oh, there are points on the graph with these x-coordinates. Yeah, no problem. Yeah. So it kind of looks like anywhere I go on the x-axis, there's a point on the graph with that x-coordinate. Once again, I've left off the arrows. It's my flaw. I don't like to do it. I think the graph looks messy. But what that tells me is that even though I see only a part of the picture here, this graph goes on indefinitely in both directions, right? So what I'm seeing is there actually isn't a value on the x-axis that isn't in the domain. There isn't a value on the x-axis that doesn't correspond to a point on the graph. No matter what point I pick on the x-axis, I can find a point on the graph with that x-coordinate. So what that tells me is the domain of this function is all real numbers. Okay. Well, let's think about the range. Right, so the range is the set of all possible outputs. So we do the same thing that we did with the x-axis, but along the y-axis this time. And what you're going to notice is, kind of like you noticed with the x-axis, no matter what point you take on the y-axis, there seems to be a point on the graph with that y-coordinate. Right, so, and so on. Again, the graph goes on forever in both directions. So much like it turned out that the domain was all real numbers, the range appears to be all real numbers too, because it appears that any value of y that you pick, you are going to have a corresponding point on the graph So any value on the y-axis, meaning any real number, is a possible output for this function. So there it is. Is that the one you guessed? This is the function with both an unrestricted domain and an unrestricted range. So now we have problems 2 and 4 left. We're going to go over both of them, but what I'd like you to do is I'd like you to pause the video and give yourself a couple of minutes, maybe 2 minutes. Think about what would the domain and range be for the function whose graph we're looking at in number 2. So again, pause the video for 2 minutes. Think about it, jot down what you think the domain and the range are, and then we will resume. All right, welcome back. So what did you think? What did you find? Let's walk through it. So when it comes to domain and range of functions from graphs, I like to be very tactile. I actually physically like to trace along. Oops, is my Apple Pencil not working? Oops, give me 1 second, I'll plug it in. So I like to physically trace along the x-axis in order to be able to see what the situation is with my graph. So as I trace along the x-axis, what you see here is, sure enough, there are points on the graph for any value of x that I pick. I want to remind you again that even though I don't like to put arrows on my graph, unless otherwise indicated, assume they're there. So this tells me that this graph continues to go on, and it gets very tall, right? It gets really, really steep quite quickly. So if you pick a value of x out here, the y-coordinate of that point is really big. It's way up there, but there still is a point on the graph with that x-coordinate. By that same token, if you pick a point here, right, the value of y is probably up here somewhere, so it's beyond the scope of what we physically drew, but almost imagine like if we could zoom out, if we could look at a bigger piece of this graph, we would be able to see taller values of y. This is another limitation of graphs. This is another place where having the algebraic expression that communicates how the function assigns outputs to its inputs is handy. It's useful because I don't need to make too many assumptions. I can just, well, plug it in or solve an algebraic equation, which I have some concrete tools to do. Nonetheless, it seems convincing. It seems reasonable to believe the domain of this function is all real numbers. You'll notice this isn't that uncommon. Now let's talk about the range. Well, the range of this function, we're going to do the same thing. We're going to trace along the y-axis. And wait a minute. There isn't a point on the graph with this y-coordinate. In fact, it's not until we get here that we have the first point on the graph with that y-coordinate. So much like the range started at 2 in problem number 3, it looks like in this problem, the range starts at -3. So the range starts at -3, and then from there it goes on forever. Once you've passed -3, there is at least one point on the graph for every single one of these y-coordinates indefinitely, right? Like you can see, there they all are, okay? So this is an example of a function whose range is all real numbers greater than or equal to -3. Okay, now try pausing the video for a couple of minutes, maybe 2 minutes, 3 minutes, and try tackling number 4 on your own. See how you do. After a couple of minutes, turn the video back on and we'll walk through it. Okay, how did that go? Welcome back. Let's talk about domain and range. So the domain, again, we're going to trace along the x-axis and there doesn't seem to be a problem. No matter what value I take along the x-axis, there is a point on the graph with that x-coordinate. Sometimes it's below the x-axis, sometimes it's above the x-axis. That doesn't matter. The point is, for any value I pick on the x-axis, there is a point on the graph with that x-coordinate, which means that any x value is in the domain. So the domain of this function is once again all real numbers. Not terribly uncommon. But now for the range. So I'm very curious what you all thought about the range. If we do the same thing, right? So if we kind of trace up along the y-axis, so far so good. Oops. Like for a long time there, you're totally fine. Sometimes the point is to the right of the y-axis, other times it's to the left, but then you get here. So you'll notice I included this red dotted line to guide you, because what you see is that there are y-coordinates like super close to this line, and there's still a point on the graph where that's its y-coordinate. But this number here, that's 4, there isn't actually a point on the graph. It appears that the graph gets closer and closer and closer to points whose y-coordinate is 4, but it never actually gets there. It approaches it, but it doesn't get there. So in this case, if we wanted to say it in words, we would say the domain is all real numbers up to 4, but not including 4. So up to, but not including 4. Now you'll remember I just casually dropped the word asymptote in our last lesson. That's because I want to sort of prep you for it when we start talking about it in earnest. This is another example of a function that has an asymptote. This is a horizontal asymptote, and this is an example of a function that gets really close to a horizontal line, but never crosses it. There are some really, really important types of functions that exhibit this sort of behavior, and we're going to be talking about them more in future weeks, not this week. So that's our little workshop on domain and range from the graph. I hope that you were able to do well, and I hope that your confidence level grew through watching this. You'll notice that you do have some problems in your homework. I believe homework 6 this time that deals with, hey, here's a function, here's its graph, determine its domain and its range. So our next video is in fact going to be our last one, and it will be on graphing piecewise defined functions. That's all I got for you for today. See you soon. Bye.